Recording is rolling. So welcome to Tuesday, October 19th. You guys remember yesterday we started a new section, energy and energy conservation. Okay. Uh, so uh, just in the first few minutes of class, or a few minutes in the class now, I played you guys some video demos from Paul Hewitt. You guys saw the pendulum. Right? He had a bowling ball and a pendulum. He's talking about, yeah, guys, at the endpoints, here, to sketch up what we did, just make sure you guys are following what he's talking about. Because we're going to come back to this idea. So let's make a model right now. Okay. You guys saw the bowling ball swinging back and forth like this. Uh, at, um, at the endpoints, the bowling ball must have 100% what kind of energy? Potential energy. 100% potential energy. And I'll represent that with capital U, right? Potential energy. So at the bottom, hey, wouldn't it be convenient if we defined this bottom point as having height 0? So that maybe this potential energy, mgh, right, that height could be represented by the distance above that lowest point, couldn't it? Couldn't that be h, right? Remember I told you guys yesterday that when you're dealing with potential energy, you're allowed to, this localized version, mgh, you're allowed to define the floor wherever you want to. And the floor in this case, well, the floor, like ground level, just the lowest point above, just by definition. Uh, how about right here, what kind of energy? Wouldn't it be 100% kinetic energy, which is 1/2 mv squared? Now, why is it 100% kinetic energy? Because we're defining the height 0 at that particular point. Okay. Yeah. But the total energy is conserved, so it's same number of joules everywhere in the system. Like at this point right here, it might have a mix. In fact, if it's exactly halfway up, let's say this is like height h up to this point, height h. Okay. What if this is at 1/2 h, like h over 2, like height up? Okay. Wouldn't it have half of its potential energy and therefore also half of kinetic energy? So it'd be like a 50-50 split, 50% potential energy, and then therefore must have 50% also kinetic energy. And you could plug in equations and solve for like how mass is going at that point, something like that, right? Okay. Now we're eventually going to take this, not right now, but probably in the future, is if you know the length of this pendulum and you know the, let's say the maximum angle from the vertical, do you think you could in principle, maybe with some geometry, also incorporate geometry, incorporate conservation of energy, solve for the maximum speed at the bottom? I bet you could. I'm going to plant that idea. So yeah, if you guys want an extra physics problem to think about, probably eventually going to come back and solve that. Another thing you got, and then you guys saw the pole jumper example, which is very similar to Galileo dropping the ball off the leaning tower. You guys saw Domino's chain reaction, so you could line up all these dominoes. Now to lift them, or you have to lift them against gravity, so it takes some work to do that, doesn't it? Like force times distance moved up. So you're putting energy into each of these blocks, each of these dominoes by lifting them. That's called potential energy. Then they're just sitting there like potential to do something else. He took this little tiny one, and then there's this chain reaction, and they all fell over. That turn that potential energy into other kinds of energy, like kinetic. Quiz update. So where's you guys turned in your last quiz yesterday, and unless you were absent or for whatever reason you didn't get it in, so pop in the grade tray and I'll grade that and I'll get that in. Okay. But if you did turn in yesterday, I did get grades uploaded by about 11 or 12 last night. Here's what I have to tell you guys about this is I tossed out 2 questions. I ended up tossing out the this one. I did want to see how do you guys handle this, what you did with this, but in retrospect, I should not have put this on here because this is more related to what we're just studying right now. Okay. So number 4, I did omit that one. Also, I think some of you guys caught this, but number 8, number 9, I referenced the centripetal force lab. I said, suppose you change one variable, how would that, how would another variable respond to maintain balance? Okay. Number 8 was perfectly fine, but some of you guys caught, there's actually a mistake, a typo in number 9. Do you guys catch what it was? If you quadruple the weight from 100 grams to 400 grams, what's wrong with that statement? Yeah, grams doesn't measure weight. Grams measures mass. And weight is measured in what? Like newtons, like newtons, millinewtons, some version of that. Okay, so I did see it. So I mean, because I mixed up the units, I have to toss that one out too, because that one is not phrased correctly. So there you go. Toss out number 4, number 9. Went ahead and just gave you guys the points for those. But yeah, it's fun to see how you guys feel about this anyway. Right, so stuff we're doing today, got to finish the energy notes with you guys. I'm going to derive escape speed with you guys, show you guys how this universal form of potential energy that I showed you guys at the tail end of class yesterday actually simplifies to the localized version. Tell you guys about this new variable unit, power in watts. And then near the end of class today, do you guys have a packet like this on your desk? Packet like this? Okay. Yeah, oh yeah.
What would the answer been to number 4 on the quiz?
Oh, number 4 on the quiz. Tell you what, that is a good question. What is the answer to number 4 on the quiz? I'll come back to that in the future. So if still get some papers in, I'm not gonna grade it, but yeah, we'll come back to this. So if you guys think a bit more about that, I'll release the answer key too once I get it. Once I get all the quizzes in. Right, so this page here got a bunch of different scenarios, and then we'll do some conservation of energy setups for like all these different scenarios. Okay. There's also some conceptual questions I did on the back here. So I'll get to that by the end of class today. Okay. All right. So a quick recap of everything you saw yesterday. Energy measured in joules. 1 joule breaks into fundamental units like this. Right. Then we were looking at what I refer to as like building blocks of mechanical energy. That's sort of my different colloquialism for this, but there are different energy forms, more than just the ones we're going over, but these are the ones that matter for this class. So work is force times distance. Now, really, this is an energy transfer, but you can sort of treat it like as one of these energy terms. You just put it in the equation and it works out okay. Now, importantly, it's the dot product, so only the parallel components, so sometimes written like this. Okay. And then that's what the shopping cart example is for. So if you push at some angle, only the force that goes the same direction as the push matters. Only that component matters, right? So dot product. Okay. A sort of counterexample, or maybe extreme example, this is what if you carry book horizontally across the room? So if you're applying an upward force to hold it up, but you're moving it horizontally, there's no work associated with that because those vectors are perpendicular to each other. Okay. But if you apply a force upwards and move the book upwards, there is an energy transfer associated with that. There's work you're doing on the book to lift the book. And so you just multiply force times distance for straight up because they're parallel to each other in the same direction. Force and displacement are. Okay. Which leads you exactly to potential energy, the localized version, which is the form you use almost all the time anyway. Okay. Because if you think about it, the force you have to apply would be equivalent to the weight. The distance it moves is the height. So the work you do on this book, well, that's the energy you're giving into it. So that's the energy it has at the top of some ledge, MGH. That's called potential energy. Just like those dominoes, as they were standing there, that energy was stored ready to transfer to something else. We looked at a couple of graphs. So force versus distance graph. The area underneath that curve represents work, like an energy transfer. Okay. Notice the units of those axes. This is one of those general principles I always come back to. Because someday you guys are probably going to see graphs that you've never seen before in your life, but can you know how to navigate a graph, how to work with the units of the axes, right? Newtons times meters, that has something to do with the area, doesn't it? Which is also some number of joules, right? Okay. And then we took this and said, well, let's do a slightly more complicated version, Hooke's law, right? But same principle applies. The area under that curve also represents the work done to compress it, and therefore the energy stored in the spring. That leads exactly to this setup. Energy stored in springs 1/2 kx squared. Okay. I told you guys kinetic energy. This is energy in motion. Anything that's moving has, well, you can express it like that, 1/2 mg squared. Okay. How much kinetic energy it has. Okay. We looked at a basic conservation of energy setup. Galileo dropped something off a cliff. Okay. Now this expression here, sum of energy initial equals sum of energy final, for a closed system. And that means a system that has no outside forces acting on it. Okay. This will be true. Energy will be conserved. So you can say potential energy here, kinetic energy here, solve for V, square root 2gh. Okay. Same thing as you would have gotten from kinematics information a long time ago. Right. Oh, that's what I was showing right here. Okay. And then near the tail end of class yesterday, I set you guys up with one. Well, okay, this is going to lead into where we're starting today. We're going to pick up from. Right. If you think about, go back to potential energy, MGH, works all fine and good, right? Except that G is only true at the surface of some planet. If you get too far away from the surface, either tunneling down or going away from the planet, then that G changes. So there must be some more universal way to express potential energy, and it's this right here. Right? So where are we going with this? Let's explain sort of where this comes from, like what GMM over R. Why is that? Why is it negative? Right? And negative is a part of it. Okay. So it's around. All right, so you guys remember how work is equal to force times distance? Right? Well, dot product. Okay. And the work you put into something like lifting it, that would be the potential energy that it gets. So I'm going to say that U, potential energy, maybe gravitational potential. We're looking from a universal point of view. Well, from a universal point of view, isn't force universal gravity constant times the two masses multiplied together divided by the distance between them squared, GMM over R squared? That's force, right? Okay. And then distance. Well, hey, I see a distance variable already in here, right? Which is some value R. So like, what if you were to lift it to like that location, something like that? Maybe we could like multiply by R. Hey, isn't one of the R's going to cancel? Right? So that would be something like GMM on R. Right? But there's one more detail, which is I threw in a negative sign. What's the negative sign about? Okay, now this one you have to think deeply about, but I'm going to do my best to explain this. Okay? Suppose that there is a giant empty section of space, like nothing around, like a big old, I'm going to call this, maybe like almost empty universe. This is kind of a crazy example, but best way I can think to explain like where the negative comes from. Okay? And let's say on one edge of this otherwise empty universe, there's a planet that has mass m, capital M. Okay? And on the other side of this universe, there's a little tiny lab weight with mass little m. Okay? And they're separated by some enormous distance that's like almost infinite, just crazy big distance, right? In fact, they're so far apart from each other and not moving relative to each other that while there be maybe like no kinetic energy associated with the system, that you might just say no energy at all, wouldn't you? Like, how much mechanical energy is in the system? Well, like none, right? So we're going to start off with 0 joules of energy in that system. Okay? Now, if that's true, then well, let's start with that. Okay? I'm going to say that. Yeah, let's set up an energy conservation principle because I want to show you guys. At the same time, I'm explaining this negative. I'm going to show you guys where escape speed comes from. Okay, so it goes hand in hand with that. Okay. Sum of energy initial equals sum of energy final, or point A to point B, or just within in a closed system. This would be a closed system. Okay? There's no outside forces. Okay? Now, there's an internal force. There's a gravity force between these two. Maybe you feel a tiny, tiny, tiny tug on each other. They start to fall towards each other. Okay? Now, the planet's so massive, it moves a little bit, but mostly it's the lab weight moving across space. Right? Maybe they meet like, boom, like right there or something. So I said there was 0 joules in the system to start out with. So it's sort of a definitional thing, right? Okay. Now, as they move toward each other, and really, again, it's mostly lab weight on the move, then, well, isn't that lab weight, say, picking up some kinetic energy? Capital K, that's kinetic energy, right? Okay. And as it's getting closer to the planet, well, getting closer, like falling towards something, is not like losing height relative to that thing. So there is some potential energy involved. So I'm going to say plus U. Right? But the energy in the system was sort of like defined as like 0 joules to start with. Right? Hang on a minute. If I got two things added together and they add up to 0, then doesn't one of them have to be negative? Right? And it's not going to be kinetic energy because one has to be squared. Right? B squared, well, that's positive. Mass is positive. Right? So it's got to be potential energy. So from a universal point of view, that's why potential energies are always treated as negative values. Okay, okay. So I said this is going to lead to escape speed. So let me show you guys how. Okay. Let's plug in some formulas. So 0 joules is equal to got 1/2 mv squared plus g M on R. Could be something like that, right? Okay. Now, what about this though? If this lab weight is falling basically from the edge of space and it crashes onto the surface of this planet, let me throw in one more attribute of this planet. Let me get radial size R. So radial size R. Okay. When it crashes into the surface, how fast is it going to be going? If you dropped it from the edge of space, is it going to be going infinitely fast? I mean, it fell across like the universe. Right? It took billions of years to crash into the planet. How fast is it going to be going? So it is a finite speed, and we can calculate it right here. Because all you have to do is take this setup and say 1/2 mv crash squared, so the crash speed into the planet, okay, at a very specific radial distance from the center of the planet, and that's capital R, the radial size of the planet. Okay, see that? Let's solve for that crash speed. How fast is this lab weight crashing into the surface of that planet, falling from the edge of space? Okay? This conservation of energy setup can solve for us. So, I'm so sorry. I have a little mistake. Guys, what's the mistake? Yeah, oops, I'm so sorry. I forgot the negative sign. Okay. So then when you add this over, okay, now everything goes positive again. So I got 1/2 mv crash squared is equal to, now it's positive gmm on R because you just add that term over. Okay. So, what's going to cancel on both sides? Yeah, the mass of the lab weight goes away. Okay. And then I'll cross multiply up to 2, take the square root. Looks like v crash is going to be the square root of, well, that'd be 2gm on R. Hey, does that expression look familiar? What is that? That is escape speed, isn't it? I know I swapped out all my posters, but this is escape speed. And you know why? Because think about it this way. If this lab weight fell from the edge of space and crashed into the planet at exactly this fast, and just pop in some numbers, mass, radial size of the planet, then wouldn't that also represent the speed you'd have to throw this straight upward from the planet so that it could go all the way back to the edge of space before it came to a stop? Right? That's what that is. So this is also escape speed, just in the opposite direction. But it's the same magnitude. Okay? So that's how you derive that. That's where that comes from. Okay? Comes from, well, conservation of energy using universal gravitation. Okay. All right, you guys get that? All right. Now here's where I'm going to do something a bit more technical with you guys. I want to show you guys why GMM over R, or negative GMM over R, okay, simplifies to MGH at a local level. Right, you guys ready to see that? Okay. So this is another one of those things that takes some deep thinking. So here we go. Why does negative GMM on R simplify to MGH at, well, at a local level? By local, I mean like at the surface of a planet, like local to the surface of a planet. Huh. All right. Well, check this out. So, let's get a picture going like this. Say you got a planet, and it's got like a big old mountain on it, maybe something like that, right? And yeah, maybe there's like a plateau down here or something. I don't know. Right? So there's some radial size to this planet. They will call that capital R. Oh, I know what I should do. Let's get like a little valley or something silly. Okay. And what if you went from the top of that mountain, I'll call it R2, to the bottom of this valley, I'll call it R1. Okay. There is a height difference between those two, isn't there? From there's a change in altitude from that dashed line to that dashed line. Is it R1 to R2? Okay. But in terms of like the radial size of the planet, it's not very big, that height change. Okay. I might call it height change H. H, right? So that H is equal to the difference between R2 and R1. Okay? Hold on to that idea. That's going to come back. Okay? So what is the change in potential energy from the top of the mountain to the bottom of the valley? Okay? So the change in potential energy, well, that would be the energy at the top minus the energy at the bottom, right? So that'd be negative G M M. So here's the mass of the planet. Here's the mass of the thing, whatever, right, whatever. Divided by R2 minus negative G M M on R1. Wouldn't that be true? Right. The difference in potential energy is just potential energy here, potential energy here. Take the difference. Okay. Hey, these fractions look pretty similar. Now they have a different denominator, so let's get a common denominator. Can I do that by multiplying by R1 on R1 and multiplying by R2 on R2? I could do that, right? It looks like the negative is going to cancel also, so it goes away. Is that? And you know what? While I'm at it, maybe I'll also do this. Take the positive one and move it in front, just because positive minus negative. Okay. So the change in energy would be, see, G M M R2 minus G M M R1, all divided by R1 times R2. Isn't that true? Just a little bit of math here. And there's a lot of stuff in common in the numerator, so I'm going to factor that out. I'm going to factor out, so change in energy, potential energy, I should say, is, okay, there's a whole GMM I could factor out of the top. Okay. R1, R2, okay. And then inside here, I've got R2 minus R1. Okay. Is that okay so far? Okay. Now, if the height change is not very much, now here's where the locality comes into play. Okay. R1, R2, and capital R are very similar to each other. Okay. So R1 is approximately the same as R2, is approximately the same as the radial size of the planet. Not exactly, but see this picture? See, they're pretty close to each other. Okay. That's part of the trick to make this work. Because what I'm going to do now is make a substitution. Okay. Let's do a couple substitutions. So the change in potential energy is, okay, so GMM, the denominator ones, let me say, well, those are approximately the same as each other, is approximately the same as the radial size of the planet. Could you just call it like R squared, approximately? Okay. No, maybe I should say equals exactly, maybe I should say equals approximately. Okay. And then, hey, R2 minus R1, that's just H, isn't it? So this is H. And, oh, GM over R squared. What's that equivalent to? Universal gravity constant times the mass of the planet divided by radial size squared. You guys remember this from last week? That's lowercase g of the planet, right? That's the gravity strength of a planet, the gravity field on the planet. Right? So then you put it all together, the change in potential energy from the top of the mountain to the bottom of the valley is, well, let's see, I've got the mass of that object, whatever that was. I've got gravity field, and I've got a height. Hey, look at that. No, I should say approximately equals mgh. Yeah, so the change in potential energy is mgh. Right? And then if you define like some height 0 as like 0 potential energy, then your potential energy at some point could be just mgh. All right, guys ready for next set notes? So power, you can think of like a rate of work. Remember what work is, it's like an energy transfer. So maybe you can think of it that way too. Rate of energy transfer. And just spelling out those words, I bet some of you guys can start to piece together the formula. So power is equal to, well, rate of work, rate of energy transfer. You guys know that rate change of location, rate change of displacement, that's velocity. Rate change of velocity is acceleration. So rate change of something isn't just that thing divided by time. So isn't this like work per time? Okay. How much work did you do? How fast did you do it? Like what time interval? How fast are you doing work? Okay. And you guys have formulas for that too. So like work and time. Okay. You know what? Go here. hold off on that. Gonna come back in, say something about that too, but, here, power is measured in watts. What is 1 watt? Okay, well, 1 watt, this could be capital W. Okay. Now, capital W, you got to be careful because as a variable, right, what does capital W stand for? Not watts, but yeah, it could be work. Right? I usually spell out work, but a lot of times on AP exams, they just print the letter capital W. So you have to know the context of these things. If it's as a variable, capital W is work. As a unit, it's watts. And so work measures energy work is measured in joules. Power is measured in watts. Okay? But what is 1 watt? Well, follow this format right here. Like work is some number of joules. Okay? Time is some number of seconds. So, okay, so 1 watt is 1 joule per second. Right? And a classic example of this could be a light bulb, couldn't it? Because you guys have probably all seen on a light bulb, say there's a number printed at the top, it says something like 40 watts, like a 40-watt bulb, something like that. Right? Oh, that means 40-watt bulb, that is telling you the rate that it's pulling energy off the electric grid. It's pulling 40 joules per second. Right? That's what 40 watts means. Right? That could be a constant value. Right? There would be a power plant that supplies that energy on the other end, and it's supplying that energy at some rate. Right? Maybe like a nuclear plant might supply more watts than a hydroelectric dam or something like that. Okay. But what is 1 joule? Well, you guys know 1 joule is kilogram meter squared per second squared from yesterday. So then put this all together. In terms of fundamental units, it looks like this. Kilogram meter squared per second cubed. Okay. That's a way you can quantify what 1 watt is. Okay. 1 watt is that. Okay. Is that right? All right. So I want to go back to this expression here. Power is work per time, and what we've utilized that already just to make sense of the units. But there's another place I want to go with this because there's actually a really handy formula that is not on the AP equation bank. That is, well, could pick you up a couple of points. I wouldn't be surprised if it. You guys ready to see a formula that's not on the equation bank? AP's equations. Okay. So I'm going to pick up from this point. That power is work per time. I'm going to rewrite this because you guys have a formula for work. Isn't that force times distance, right, for work? And then, okay, so divide by time to turn it into power. So that could be that, right? But you know what? If you stare at that long enough, you might see a different way that you could group these variables together. I mean, you could go just work backwards, like force times distance, that's work, and then just turn this back into this. Or do you think you could group these somehow differently? Like, what is this right here? That is velocity, isn't it? Hey, can you guys memorize this going into the AP exam? Power is also equal to force times velocity. Okay. Force times velocity. Okay. So for example, like where could you possibly see this? Okay. Suppose there's an elevator. Okay. And let's even do like a free body diagram on this elevator. Okay. So this elevator maybe has a weight, mg. Okay. Maybe there's a tension in the elevator cable pulling it up. Maybe that tension is equivalent to the weight, so it's moving at constant speed. Okay. Or maybe the tension is greater than the weight, in which case it's accelerating upward, either moving up faster or moving down but coming to a stop. Right? Either of those could be. I don't know. It's generic case. Right? Actually, you know what? It should be a simplified example. Okay. Well, either way, but can't change this to make this the same magnitude. Let's put this in equilibrium. So maybe the elevator is going constant speed. It doesn't have to be, but that could make this a little easier. Okay. Constant speed. Let's say there's a constant speed upward. Okay. Notice the free body diagram. All the forces are balanced. Okay. That would allow constant speed. I wonder what is the power associated with the motor at the top that's cranking that cable and pulling up, right? Because you have to feed energy to that motor at some rate. And that would represent power. Hey, can it just be this? Okay. Whatever the tension is in the elevator cable. Okay. This is a tension force. a lot of times I just say capital T for tension. AP, I think, tends to prefer F sub T. So if you take that tension, just feed it in there, and take the speed of the elevator, feed it in there, you could get the power associated with the motor cranking it up. Okay. Guys see that? Oh, all right. I think we're ready for this energy table. So just double check. Does anybody not have this packet? Okay, you guys have this? All right. So I gave you guys a bunch of different scenarios, like 3 pages of scenarios. So what is in the closed system? Now, this is one of those things that AP cares a lot about, is defining a closed system. So a closed system is just any system that there is no outside force acting on it. If there's no outside force acting on it, that also means there's no energy transfer into or out of that system, right? It's like it's contained, okay? And there's actually different perspectives on some of these scenarios that you could define the closed system differently. So as we go through these, I'll just like pick one option and go from there. Okay? What is the energy associated at point A? What is the energy at point B? Okay. And then if the system is closed, then you could equate those two. You could say the energy at point A is equal to the energy at point B. And then you could do something like solve for stuff. And that's why this last column, I just picked a variable like VB, said, oh, solve for that over and over for these different scenarios. Something like that. Okay. You guys get that? Right. Now, this first one we did yesterday. So good format to, well, good example is you guys can see the format of this thing. So Galileo drops the ball from top of the Leaning Tower. Okay. What is in the closed system? What do you guys think I should include in the closed system? Probably the ball, okay. And also the what? What force is acting on the ball? Gravity, and that comes from the presence of the Earth. Okay. So if AP asked you a question like, "Hey, what's in that closed system?" That would be the answer. Okay. The ball and the Earth. Okay. It's a ball or a system. There's an equal and opposite force between the ball and the Earth. It's a gravitational force, isn't it? Okay. That's what's driving the ball to move. Okay. What is the energy at point A? Oh, well, isn't it all potential energy? So mgh, and then the drill subscript A on that. So go do that. What is the energy at point B? Let's say point B hasn't quite hit the ground yet. It's like a millimeter above the ground, but it's moving really fast. Okay. Wouldn't it all be kinetic? All your 1/2 mv squared? And that would be at point B. Okay. Okay. And then last column says, pick a variable and solve for it. In this case, VB. Can you solve for what is the speed of point B? Okay. Okay. So now I made this last cell way too small. And it's up to you how you want to do this. So, but to expand this out, every single step on this last cell starts with a step. Right? Every single process starts with a step. Sum of energy at point A is equal to the sum of energy at point B. Okay? So sum of energy at point A is equal to the sum of energy at point B. Okay? In this very fundamental example, so we got mgh at point A turning into your 1/2 mv squared at point B, like that. Okay. Can you solve for the speed at point B? Yeah, we could do that. So the mass is going to cancel, just like yesterday. Cross multiply at the 2, take the square root. So see VB squared equals 2GH at point A. So VB is the square root of 2GH at point A. Okay. Is that all right? Okay, so I just did all the work there. So you get B is equal to square root 2GH at A. Okay, next one. A cannon fires a cannonball at some angle from ground level. Okay. So at point A, this cannonball has a speed. I'll call it V sub A. Okay. And at B, well, it has a speed too. It looks like it's just going straight horizontal. I call it VB, can I? Like that. Okay, what's in the closed system? Now, here there's a heavy implication that's just going to be, what do you guys think I should include? The cannonball and the Earth. Okay. I'm specifically not going to include the cannon because now if you rewind the clock like a second before the snapshot here, then yeah, the cannon does put a force on the cannonball, but I'm not going to start counting the system until after the cannonball has left the barrel of the cannon. Right? So I'm showing it after it's left the cannon barrel. Um, you could do that interpretation, go that way, but I'm just doing this. What is the energy at point A? Well, isn't it all kinetic energy, 1/2 mv squared? At point A. Notice I put this dashed line at that level, so I'm defining that as like height 0. What is the energy at point B? Now here there's an energy mix. That cannonball is on the move. It does have some 1/2 mv squared at point B. Okay. But it also has a height above the ground, doesn't it? So plus mgh at point B. Okay. So it's gain some height. Is that right? And then solve for the speed at point B. Right, so yeah, let's do that. You guys got, so sum of energy, so the sum of energy at point A is equal to the sum of energy at point B. You guys know if this was an FRQ question, that would almost certainly be worth 8 point just by itself, just by writing that, right? You guys know that, right? So write that line for an FRQ. Then at point A, you got your 1/2 mv squared at point A. And at point B, well, you have this energy mix. There is some 1/2 mv squared, although this speed is not as much because some of the energy has been diverted into energy of height, mgh. That's our new way of thinking about it. Oh, what's going to cancel? All 3 terms. The mass of the cannonball, which shouldn't be a huge surprise because this should be consistent with all your kinematic formulas. I mean, you guys could solve this using kinematic motion, couldn't you? Right? Could also do that. Right? That won't be true of all these scenarios, but some of these, including this one, it is. Just kinetic potential usually. Okay. This is a projectile problem. So solve for VB. Let me pull this term in isolation. So 1/2 VB squared. That's the same thing as 1/2 VA squared minus GHB. Okay. Maybe multiply everything by 2. So VB, I mean, this is just math. You guys could do the math, right? And then finally, VB would be the square root of VA squared minus 2GH sub B. Just like that. So skip a bunch of steps here. You got speed at B is square root of VA squared minus 2GHB. Is that all right? Okay. Now, something else I want to say about this problem. Right? If you look at the solution, it's always a good idea to like test it out, poke around, try to poke holes in it, see is everything self-consistent. What if the height change ended up being 0? I mean, eventually this cannonball is going to come back to ground level, isn't it? Okay. So what if the height change itself is 0? What does that just turn into? VB is just VA. Guess VB would be VA. Ooh, which makes sense, right? And in fact, VB's got to be less than VA because you'd be subtracting off something. Right? And hey, square root 2GH, that looks similar to the Galileo problem. I mean, it all seems self-consistent, doesn't it? Okay. But the other thing is that you could actually solve this problem using kinematic information. Wouldn't the speed at point B just be the horizontal velocity? Okay. And I bet some of you guys can do that in 1 step in your head. What's VB also equivalent to? This is for kinematic. Isn't it speed A multiplied by what? Cosine of the angle relative to the ground? Okay. Whatever angle this is, theta. Is it just VA times cosine theta? Okay. If I gave you some numbers on these, you could show that these two would get you to the same thing. That's 2 different points of view. You know what you have. Okay. Let's I do here. Yeah. Let's get this next one set up anyway. Okay, so kid slides down a hill of length L, and there is friction. Ooh, there is friction. So what's in the closed system? Well, I'd have to include the kid and sled. I'm going to treat as a single object because they're all moving down together. Okay. Of course, we have the Earth. Okay. Now, here's where things get a little funny. Is what about the friction? Okay. Now, one way I could approach this is I could include the Hill surface and the friction with it inside the closed system. Okay. Or I could do this. I could just have these defined as my system, but if I did that, it would be an open system. Let me do that. Let's do that approach. In parentheses, say open system. And the reason it's open is because friction is an outside force acting on that system. Okay? This is one approach. This is one interpretation. Okay. What's the energy at point A? Can you guys figure this out? Ooh. How much time we got? Oh, the bell's going to ring in a few seconds, isn't it? Okay, so actually that's probably a pretty good pause point. You guys think about that, and then tomorrow we'll do a bunch of examples.